I mean, the title of the topic is really one of the things I've been more interested in working on in the last few years. This keyword here, I feel trapped in there. This keyword, implicit regularization, I tried to make a point, is actually an old word that has somewhat been rebranded and for various reasons has become quite popular in the last few years. So in this talk, first of all, I try to curb the enthusiasm and try to say we're not really going to give you a super full theory. It's more like trying to take steps towards filling the blanks a bit. And also, remarkably, there will be zero statistics in this talk, but there is some attempt to do some kind of not only optimization, but robust optimization under a very standard worst case model. And pretty much everything is going to be worst case. So this is a few work together, but mostly with these people, especially Silvia Villa, who is in Genova. And the whole idea is to some extent to look at optimization in scenarios where there is some modeling of your data. The objective function then just grow in trees. They come out from some modeling process, and they are typically based on some observations. And the observation might be subject again to modeling assumption and then noise. And you would like to keep that into account. And the hope is that by doing that, you can be more efficient, try to spend less time doing what you need to do to get a good solution. Okay, so that's somewhat the general idea. So this is the setting I'm going to consider. I apologize, the notation is really more of an optimization notation. If you think of a basic regression problem, you're not too far away from what we're considering. There is a linear equation, ax equal y. X is the unknown, y and a are given and known, okay, at least in the very basic model. I consider dimension-free analysis, so I put Euclidean spaces of infinite dimensions, so these could be Hilbert spaces. And the basic problem is to, given a and y, find x. Okay? So that's a very basic inverse problem. And this is the setting I'm going to consider, and I'm going to add noise to it in order to make it a bit more interesting. All right, so this is very classical, and the classical problem here is what is called this ilposedness, that with the existence of a solution, uniqueness of a solution, and potential stability. Okay? And we're going to see briefly how you fix all these things classically and in a more modern way. So first of all, you say, okay, if there is no solution, I take a discrepancy that tells me how far I am from having a solution. Okay, think of least squares or a norm, an LP norm or something like that. But you can think of things like KL divergences. Some of these come from modeling assumption with respect to some kind of noise. Okay, L2 is an assumption, KL is another assumption, L1 is another assumption, more generally the LP norm. Loss functions in learning terms. And we define this solution, which is the best possible solution, in this sense, the one that minimizes the distance to the data. And then, of course, there can be multiple solutions to this. Think, for example, of a linear system which has more unknown than equations. And so what we do is that we introduce a prior information to select one among many possible assumptions. This is what is sometimes called a regularizer. And among all the possible solutions to this problem, we select the one with that minimizes this. Okay, and this is one place where it's basically where I lose a lot of my generality is because I assume this to be strongly convex. Okay, the reason why we do this is because essentially, in a worst case scenario, if there are many solutions and unless you make more assumption, this is the one way to get. I guess you need strictly convex to get one unique solution, strongly convex to give us a bit more juice in terms of getting rates and so on. Okay, the big guy that is missing here, say, is just a pure convex term like L1, in which case the solution will be not unique, but then you can make assumption, blah, blah. I'm going to comment it in the end because, for example, Patrick and his students have been working on this. All right, so this is the basic scenario, and this essentially fixes existence and uniqueness, but not stability. Why? Well, the idea is that in practice you will not have access to y, but only to a perturbed version of y, and here I'm making this non-statistical assumption, which is kind of worst case, which is that I just live with a vector which is in a ball around the true datum. Okay, so y hat is just a corrupted version of y, and delta is how far away it is from the true one. Okay, so the idea is that's what you're given. You want to be too robust to it, so you want to find a stable approximation of x dagger. So you would like to do this, but you cannot because you don't have the true y. And so you can look at kittens. And so suppose that this is the true image. Suppose that, for example, let's assume that A is a blurring operation. So you get a blurred version. And then, this is what you get if you solve this. Then you put noise. This is salt and pepper noise. And then you could say, okay, I'm just going to do the same thing on the noisy data. So the only difference, if you look carefully, you see that the hat appears here because the hat appears here. Okay? And what you get sucks, pretty much, okay? Essentially because the problem is unstable to noise, and this is what you get, okay? It's not a good solution. So the idea is that you want to be able to somewhat get something more stable than this. All right, so again, very quickly, because here I'm just setting the notation pretty much, you can look at penalized version of the problem. You relax the problem, you relax the constraint, you introduce a relaxation parameter. I put it here for the sake convenient later. And then you have to try to find a trade-off. And now, of course, you don't have a problem, but you have a family of problems. You have to select the best possible lambda, and there are standard results that tells you, for example, that in this setting, you need a little bit of further assumption. Existence of a solution is not enough to actually get the rate. You need a little bit more, a kind of a qualification or certificate condition. And then you can get a bound for any lambda. Basically, you have a stability term and then a convergence. So you want the lambda when you have exact data to convert to the true solution. So you have two terms. When lambda goes to 0, you go to the right place, but then you have to choose lambda in some kind of stable way. You trade this off, you get lambda depending on delta, and then you get the bound. Okay? And this is a pretty general result. Here I just give you the latest version. There are many, many classical results about this. Okay? And this is good. This is a good bound. It's not improvable unless you make further assumptions. So if you're shooting for this, you're shooting for the best. In the worst case, yeah.
Well, what was on the previous slide? What were you using for R with the kittens?
I think in that case it was probably a TV-like thing.
Okay. I guess I understand why this would be so much worse than Tikhonov, for instance, or the regularized form on the next page. Are you trying to contrast these two, or?
Well, so this is the lambda equals 0 version of the other one, right?
Oh.
So this is just this guy. So it essentially corresponds to the limit. Well, I guess lambda going to.
Okay. No, I get it. Okay.
Okay. So it's just the 0 regularization version of that. Yes.
Question: do you have a rotation or something on the?
A rotation.
There's a big white spot with the dimension.
Here.
Yeah.
Yeah, I don't know what's happening there. I still see here are their legs and here are the stuff. So.
Y hat, so you see the blurred image, no?
Yeah. Yeah. Y hat is the blurred. So this is just the blurred images, and these are the blurred noisy images. So the difference between these and just noise. So it should be a bit less white. I have to double check. As you might have guessed, there's not going to be a striking empirical result in this talk. All right, so I guess the main point of this is some of the turning point is that this is all story. You can also derive these algorithms for 13 different points of view, Bayesian, non-Bayesian, you name it. I guess the one point is that this is, if you enter optimization conference, this is an algorithm is a problem, and half of the people think about how to solve this, okay? And they don't even know why you do this, but well, I guess a lot of people they do, but maybe they don't care so much because they just want to solve this and they worry about efficient way to do it. So what do? You typically do the following thing. You pick an interval of potential value of lambda, you discretize it somehow, and then for each value of lambda, you compute a solution, and then you use some validation criterion to pick the best possible lambda. And for each lambda you try, you have to solve an optimization problem, okay? And typically there is a smart way to do it, which is maybe you choose, the cheapest lambda, okay, and then you use this to restart the computation, what is sometimes called warm restart. I'll get back to it. So, again, the idea here is that there is a path of potential solution that drives from initialization. Different lambda get to the best possible noisy solution, but you want to get close to the non-noisy solution. So you have to find lambda, and that's the basic idea. So there is a lambda here, which, going back to your point, is going to be better than this. Okay. All right. So this is all news. Okay. So this is a basic setting and a basic approach and a basic way to solve it. And I guess maybe the emphasis here is on the fact that when you have to do this, you have to solve many optimization problems. Okay, multiple times, and typically you have to go up to convergence unless you make some smarter observation. So an old idea is called iterative regularization, and the new name is implicit regularization. So to try to be trendy, I put it in the title, but then pretty much everywhere else I try to be faithful to the fact that this is the idea from the 1950s, and so I often use that too. So what's the idea here? Let's go back to this, okay? And then solve this iteratively. So you don't relax the problem and then solve it. You just solve the original problem with the noisy data, and possibly you stop it early if needed. That's the basic idea. Okay? So why should it work? Well, first of all, again, there is a lot of literature in this for Euclidean norms and Hilbert spaces, really from like 70 years ago and on. There is a lot of literature on this when this is a Banach norm, but under some stringent assumptions that don't cover a lot of cases. And then into the 2000s, especially Stan Osher and Martin Berger spent a lot of time thinking about this. And they mostly had like convergence result, but there is really a lot of literature. And then here again, I just put a random selection of friends' name and other people. But really, in the last few months, I guess, the idea of implicit regularization became extremely popular because it seemed that maybe it unveils some of the way we use neural networks these days, and the optimization procedure underlying the training, the optimization of neural network, leading to specific solution, not just any possible solution. So here I refrain from that and I let Francis take over. So again, like a cartoon of what does it mean to do implicit regularization in I guess in a top-down way, okay? So you know what you want to solve, it is this. You design somehow an algorithm to solve this, okay, exactly. And then you simply do the same algorithm where you replace the datum with the noisy datum. That's it, okay? You don't relax, don't you add the penalty, you just solve this problem here. What's the idea? So let me call xt this idealized iteration and x at t the one that you can actually implement. The idea is that xt is going to go to the right place. It's an optimization algorithm to solve the real problem. You cannot implement it, but theoretically you can prove it goes to the right place. And then you have to study how stable is this, okay? How far is what you can do with what you would like to do? And this is a stability term, okay? And again, this is the error propagation stability versus convergence optimization. This is the inverse problem of terminology, but you can think of if this was statistics and I just assumed the noise to be random, this would be essentially a bias and this would be essentially a variance term, okay? Okay, so again, here is my Pullman version of a movie. And we can discover where the white is coming from. So this is the optimization on the noisy data, okay? So you'll see it improves. At some point it looks okay. And then if we keep on going, it just becomes a smoothed version of this, okay? That's what it does. So the basic idea is that maybe, I don't know, I'm not very good at this, but you know, something like this would be better than just going up to the end. Again, this is true, not in general. It's true because we are taking an extreme case where the original problem was extremely unstable and there was noise. It might be that going all the way to the end is fine, and it's just a way to compute this X-Duggar that Becca was pointing at. But here we're considering this kind of worst-case scenario where instability really pops up. Okay, just converging is not enough. The problem is a bit harder. All right, so that's the basic idea. Okay. What is the advantage of this is that you see there is only one free parameter, which is when you stop. If you just design the algorithm to convert, the only free parameter you have is where you stop. So there is kind of I don't know, a pleasant aesthetic aspect, which is now optimization and variance control and imposing priors are somewhat merged in a unique step. So you don't do twice the same thing, you do it once. So I kind of like this a lot, and I've been working on this for a while because essentially for this reason. So how can you design a learning algorithm? So I'm going to give you a few instances. The first one is essentially for least squares, and then I'm going to move on to looking on least squares. And the emphasis is going to be on the role of acceleration, which is a very popular topic in optimization. So first, the basic case, and you'll see exactly where the strong convexity assumption pops in. The first observation is that, and there are many ways to derive this, but this is, to me, the simplest one. You have this problem, and we're going to assume that the solution exists, okay? So we assume that the solution does exist, but we assume there are multiple ones. You can adapt the thing when solution doesn't exist. And then you essentially rewrite this as an indicator function. This is the indicator function of y being equal to a of x. And then what you do, you consider the dual problem of this. Why? Because the indicator function just gives you a linear term. And here you see this, the strong convexity assumption tells that the dual of the regularizer, if I assume the regularizer is strongly convex, is going to be smooth. So if you do that, now you have two terms, okay? And both of them are smooth. They're differentiable. So in the dual, all you need to do is gradient descent. So very simple. Okay, you can just do gradient descent in the dual, as long as you can compute R star. Okay, R star is, and that's going to be the main bottleneck if you want to do L1. Okay, That's as simple as that. That's a very simple idea. Just as a reminder, just using basic convex analysis tools, you have to compute, again, the gradient of R. There is decomposition with A because it's a linear model. So you can use chain rule. And then remember that for a strong convex function, you can always rewrite the function this way, like a convex term plus a strongly convex term. And so these just become the prox minus the identity, okay, where the proximity operator is this. I don't give back the definition, but it's essentially a generalized version, a generalized notion of projection, okay, that only depends on this convex part. If you assume that this is the typical case, this is L1, this is L2, imagine alpha like a small perturbation parameter, and this just becomes a simple thresholding on the coefficients, okay? That's the basic example you might want to have. So this is just to write it a bit more explicitly. And so the algorithm can just be written in 2 lines. Essentially, let's say for L1 plus L2, an elastic net-like thing, a proximity and a thresholding operator plus a gradient step. That's it, okay? So we call this the gradient in the dual, or we view it, we don't call it, it is the gradient in the dual. We view it as the gradient in the dual, but you can also view it as what you might call the linearized Bregman iteration, and you just take a slightly more tortuous way to get to it. And it's essentially a version of mirror descent, okay? Where again, the main point is that in all cases, you need to be able to compute the mirror function, you need to be able to compute the Bergman divergence, and so on and so forth. All right, so this is simple. And so essentially, it was already looked at before. And you can get the result for this. So pretty much under the same assumption, you assume the discrepancy to be this. And then under the same kind of qualification assumption, of course, this depends on R, you get a very similar result to the one I showed you before. Only instead of lambda, you have square root of t, okay? So this is the optimization term. It goes down as 1 over square root of t, okay? So again, optimization / approximation. This is the stability term. You choose the stopping, in this case, there is noise, it's unstable. You choose the stopping time depending on delta, you get the result. The result is indistinguishable. This result is indistinguishable from the one you get from Tikhonov. The only difference is that this is actually an algorithm in the real sense, is what comes out of the computer, okay? All right, so that's a basic result. And again, here I cite us, but to some extent, I guess the previous results essentially didn't try to get rates, they only tried to get convergence, but I don't think the novelty is that big, to be fair. Okay, and it reduces, if you take R to be just L2, it reduces to standard result. So it's a strict generalization. Okay, so what can you do? You can add an inertial step, a momentum, whatever you want to call it. And here you see it. So this is the previous iteration, and this is the new iteration. Essentially, you need to introduce this relaxation parameter. And the basic idea is that somewhere here, rather than taking just one previous iteration, you take 2 previous iterations and you do some convex optimization of them. Okay, so I'll gloss on the details of this. But this is known to give some improved convergence rates for something. Okay, and now the question is, why do you care? Why do you want, if you want to stop early, why do you want to go faster? You want to go faster where? Okay, so but the basic thing is, if you do the theorem, what you see is that stability, so acceleration has a dual effect. On the one hand, it improves. If you remember, there was a 1 over square root of t. Now it becomes a 1 over t. This is kind of somewhat the optimization effect you expect. But also you have a deterioration of the stability. So this was square root of t, but also here was square root of t before, whereas here you get a t. So in some sense, error accumulate faster. Okay, and this again essentially is. So there is, to the best of my knowledge, there is this is somewhat spread around in the optimization literature. Okay, there is a lower bound by François Glinor and co-author, and then there are a few results that study optimization robust to inexact knowledge of the gradient or the prox and so on. And they make difference here that typically in optimization you assume that this error disappears and you optimize more. Here you keep them; they are there. They're like modeling constraints that you have. Okay. And so that's the main difference here. And technically, there are a few glitches here or there that you have to fix. The main point here is that if you replace square root of t everywhere with t, you don't get a better bound. You just get a more aggressive stopping rule. So you get the same kind of performance, but you get them sooner. So acceleration does give you benefit, but at least in this setting, is not just it's not always it's not better in terms of performance. It's just better in terms of computational efficiency, okay? And of course, there is a question, what is the best possible computational efficiency? And we know only part of it because we don't know the answer in terms of when you have noise, okay? We don't know the answer in the noiseless case. Okay. say something that I forgot. That's the main point, and we recover, to the best of my knowledge, this very specific setting was only studied in the case of L2 before this, and so we recovered that result as a special case, okay? And of course, now you can think of, you know, just as a side, you can think of 15 different other things you can do, right? Stochastic variance reduction, 15 different ways of accelerating, and so on and so forth. This is just an instance, right? So this is just the beginning of how to twitch a story and try to get slightly different results. Okay, so I think, you know, I'm going to be a bit long in this talk, but this is essentially this is something we did 2-3 years ago. And from this, again, you can go in many possible directions. Actually, the first thing we did is to try to think what you can do if you consider other error terms, rather than just essentially here implicitly we are using the gradient with respect to the square norm. We don't tell the algorithm that we want to use any other form of error. So the first thing that we try to explore a bit is to look into other notion of errors. And here the story, at least for us, was a bit bittersweet because it gets a little bit more involved, I guess also a little bit more interesting. We go back to Tikhonov, okay? The first step in the previous story, how you do algorithm design. And I just say you do gradient descent in the dual, okay? And then I studied it, okay? Here I want to do the same thing and I want to think, okay, how do you do algorithm design? And unfortunately, the story is a bit more complicated. We don't manage to just get rid of lambda completely. We don't manage to kill it at once as we did before. What we do is that we consider what is called a diagonal approach, okay? So it's relatively simple. You consider Tikhonov, and you first consider an algorithm to solve Tikhonov, okay, with exact datum, again. Then what do? Rather than fixing lambda, you change lambda across the iterations, okay? So essentially, you do an algorithm to solve a Tikhonov regularized problem, a penalized problem, but you let lambda goes to 0, okay? Of course, in practice, what you do the same thing, but you replace the exact datum with the noisy one. And of course, you have to specify a policy to choose lambda. And this is going to become a pain in the when you use it in practice. A what? Neck. In French is neck. All right, so here is a picture, because this thing actually, you do it without even noticing. That's what you always do when you solve these kind of problems. Because here, maybe just look at this one first. You have an iteration, okay? You have an initialization, okay? What do? You pick a lambda and you go to convergence, okay? Then what do? You pick another lambda, you start from initialization, and then you go to convergence. So this would be, you know, going this way, okay? Going from this initialization to this point here. So all the points here are solution for Tikhonov for different lambdas, and here's where you start, and this is path you can take. Of course, you don't want to do this, okay? What you do is that you want to go here, and then use this to initialize the next iteration, because what you do is that you hope you can do a much faster step. Then you get another, so every time you compute a Tikhonov solution, you use it to initialize the iteration to compute the next solution over, okay? And so you take this path. If you want this correspond to a specific choice of the lambda parameter I showed you before, which is piecewise constant, okay? So you say lambda it's like taking a big iteration where you do lambda for a while, then you do another lambda for another while, then you do another lambda for another while. So it's just a very specific case. And of course, one question is, can I do another choice of lambda? Can I take a more smoothly decaying choice of lambda and try to go there faster? And that was at least. Say again? You can parallelize that one. Well, strictly speaking, that way I do it no, because you need this one before you compute this one, right?
But if you don't do that,
of course, yeah. I mean, you can parallelize a lot of things here. I mean, it's gradient descent, so you can parallelize the gradient, for example. I mean, it's true, you can parallelize the different lambdas, but it's also true that if you just have, again, this is the passage before we had one lambda, so you can parallelize one lambda. Here you have multiple ones, you can parallelize them. We didn't get into that level of details. The idea is that here, if you manage to do this, you still just have one iteration. So you will still be comparing one iteration a bunch. But I agree that there is a lot of nitty-gritty details in the way you actually implement it. I'm not refraining from this. I just think this is, you could compare this to computed things like this. We're shooting for that guy to be the competitor because it's already hard enough. Okay, so in some sense, the theory covers both cases, okay, but we're a bit more interested into this. And also, we're a bit sad because we wanted to get rid of lambda at once. But here, we didn't manage. We just, our analysis, we were unable to do it. All All right, so what can you do? You can try to do diagonal, so this same approach as before. Essentially, we want to deal with the D potentially non-smooth, okay? So we're going to take, again, a dual approach. Here is the basic picture. We know that this is an approximation for this, okay, in the limit of a small lambda. And we consider the dual of this because we know it will converge to a corresponding dual, which is, again, the dual of this. So this is kind of a diagram that tells you who converges to whom and who's equivalent to whom. So this problem is equivalent to this, is the original minimal norm problem, and this is equivalent to this, and they each converge to its own one. The nice one among all this is this guy here, because this one is strongly convex, so the dual is smooth. This one is not strongly convex, it's just convex, but you can do splitting, okay? So you can, when you have a sum of a convex and a convex differentiable, you can basically take the gradient of this and the projection proximity operator of this. So that's what you want to do. Okay, again, the equation become a bit complicated, but this is just the basic idea when you have the thing that is now standard. When you have the sum of two functions, one convex and one convex smooth, you can basically take a generalization of projected gradient. So we can do it here, and then we have the extra twist to have lambda go to 0 at every iteration. Okay. This is a bit boring. Essentially, this is the basic version. So this is the abstract version, the non-computable version. You take the gradient of the dual, and then you have to take the prox of the dual of D. Of course, you can also exploit the fact that you can essentially use basic properties of proximity operator to replace the prox of the dual with the prox of D itself, because it's easier to compute in many cases, for example, for LP norms. And then you replace this with the fact that you can compute it explicit. So in the end, the algorithm just becomes these three lines, okay? And as you see here, lambda is a function of t, it changes across time. All right, so then we can try to prove results. It's more general than this. We can deal not only with loss and discrepancy that depends on the differences, but the statement became a bit more involved. I'm going to give you an example in a minute, but I'm just going to give you this one in this setting. We need some assumption on the curvature of the we need some assumption on the curvature of the error term. So it's not just any. It has to be, for example, LP norms. Uber KL is fine. And remember that I also assumed this, that is 0 and 0. And because this rules out logistic regression, okay? Just as a side. So it's general-ish, but not covering everything. And then, again, we make the strong assumption that the solution exists. And then at this point, we have, I just show them quickly because they're very similar to the one we had before, but they're a bit worse, essentially. They're worse. And the main point is the stability, where is it? The stability result. So we get the convergence rate, 1 over square root of t, so we are happy. We need the sequence lambda to go down sufficiently fast, depending on the curvature of the loss function. We don't know if that's optimal, and we certainly know that that's a pain in the neck in practice. These results is just about the stability, and is not good. And it's most likely because of us, not because of the algorithm. It should be a square root of t here, okay? And for this reason, we get a 1/3 here, okay?
Always assuming no delta through the algorithm?
Known delta.
So it's always known?
Right, so basically, yeah, so in all these, I assume it's known, and I use the stopping rule like this. So in this setting, essentially, for Euclidean norms, you can do something like Morozov or something like this. For other terms, you can do what is called Schur, and we're going to show you an example in a minute. Then it becomes a matter of what you can do depending on the loss. There is not, to the best of my knowledge, there is not a unique model selection criterion across norms, and it depends on the noise model, on the discrepancy, and so on. But for now, I'm lazy. So for some of the results, it's almost for free to get adaptivity. For some choices of DNR, it's almost for free. Sometimes they're not, and here I am assuming that I know everything.
So do you have simulation for the stability that goes with the square root, or?
Yeah, it does. I mean, this is wrong.
If lambda equal to 0, you can use your previous result now?
Not for the, not for...
But if you take lambda equal to 0,
yes.
you are doing exactly the same as the one you had before, no?
Yes, but in some sense, what you see is that in practice, what we do is that you assume So we take more this imaging point of view. So we assume you have a certain noise model. So when you put the model, say, it's Poisson noise, then at that point it goes together with a certain kind of discrepancy. So if you use the other one, you're just using least squares. So what you see, you don't use the knowledge of D anywhere in the previous algorithm doesn't know the discrepancy you want to include because
Doesn't it do better? You get square root of delta from before and get.
oh, but again, this is just wrong.
Oh, okay.
This is I mean, it's I mean I'm going to improve it in a minute. It's a bad bound.
Expectation for the next slide. Okay.
Right. If I didn't have it, I would be like, no, it's great. No. So it should be square root of t, period. I mean, and actually it was a bit more complicated than we expected. So, and to be fair, unless you go, I think the one thing to keep in mind is that if you don't get accelerated algorithm, this is kind of a toy. Because the truth is you can always do Tikhonov, accelerated algorithm, and warm restart. So that's the benchmark. Okay, that's what you do in practice. You take a Tikhonov algorithm, you solve it as fast as you can, and then you do warm restart. So until you match that, you're playing around. Okay, and so this slow algorithm is a proof of concept that you can go towards general discrepancy, but in practice you will not, hold the comparison to an accelerated Tikhonov. Okay, so the two questions are. Can you improve it? Okay, and then can you accelerate this? And that's what we want to do next. And again, so the variation of the theme from an algorithm point of view is minor because essentially you just add the inertial step, okay, according to some update of the parameter, and that's basically it. The algorithm is basically the same as before. You just add the momentum term. Okay. The analysis turned out to be a bit different. The proof we go first from the continuous case to the discrete case, so it's a bit more interesting. But maybe I'll just show you the result. And the results are in the same spirit the one I show you. First of all, this is just I split them. So this is just a convergence result. Again, it's very similar to before, and you need this. You get this accelerated convergence rate. And if you wish, as before, I didn't point it out, but the strong convexity constant appears both in the choice of the step size and in the rates. Okay, so it really everything we do blows out in the convex case. And then you can do stability, and here I'm going to make a long story short because it gets a bit technical and perhaps a bit beyond the point. The main observation, how do you treat this? Basically, you have to go and recycle the literature on inexact prox operator. Okay, you assume that you have this kind of assumption, so it's pretty natural. You measure distance in the discrepancy you have. You put a p so that you can have some p conditioning, basically. And then what you see is then in the only place these make an appearance in the algorithm is in the computation of this prox operator. Okay, so it's the only place. So if you assume that you don't have knowledge of the exact datum but only the noisy one, you're basically dealing with an inexact prox operator. Okay, you cannot compute it exactly. You would like, but you cannot. And so this has been a subject of topic in the what is called the golden era of convex optimization, so a few years ago. And so there are quite a few results. And again, the main difference, there are a few technical differences, not completely straightforward, but the main difference is that here the error stays. It doesn't go away. And typically was the mindset, it was to let the error go away. So we basically dig out those results. And again, here it gets a bit messy, but essentially there is several notion of errors on the prox. One is additive, one is how much you violate the prox definition. There is one that has both, and then there are two that has only one of them. So the first one is the most general one, and then you have the other two. And I'm showing all of them because essentially I'm going to give you a theorem for this. But then the two main examples of loss functions, say LP norms or additive loss functions, and KL are going to satisfy different assumptions. Okay? So additive loss function, what I mean is that the one that depend on difference are going to satisfy the type 3 error. And so they typically, you can think of them essentially as the usual LP norm. But for KL, which is basically the one that drove us down in the estimates under case, we don't get such a clean dependence on lambda. It actually depends on delta, the noise. It also depends on lambda. Okay? It actually depends on the shape of the parameter. So in the algorithm, this is going to be a lambda t, and it's going to go away. So in some sense, it's not such a clean distinction between noise and these algorithmic choices. It's more intertwined. And in this case, we don't know if it's our limit or if this is more of a fundamental fact for this kind of loss functions. Then you can get, again, a generic results for type 1 errors, and then you can specialize them for type 2 and type 3, and essentially this is, say, LP and KL, okay? All right, so for this distance-based loss function, you get the result is easy to state because it's the same one as before. The two main points with respect to before is that, yes, we can improve the previous result. We do get the right dependent. Here is not square root of t square root of t, it's 1 over t, so we get everything fine, and we get the optimal rate, okay? In the case of KL, it gets a bit more interesting because you have to choose a specific choice of lambda, and as you expect, this choice of lambda for the first time it does appear in the actual results you get. Before, we only need to make it going fast sufficiently fast, but then it didn't appear in the final results. Here it does shows up. It does show up. All right, so and it's the same exact effect as before. All right, so this is pretty much everything I wanted to tell you about. In practice, you can do, this is, what I'm going to show next is just a couple of pictures, we play a bit with it. I don't think we didn't make it, I think, work well enough to actually make a serious effort to make it into a tool. But we tried to get an idea of how hard was it to use it. So we compared to warm restart, we tried to fix a budget of computation and just choose essentially a path here, and in that case an exponential choice. And here we consider a simulation situation where we do know the true image, and we just try to get choose the parameter cheating and knowing not only the noise but also the true image. And then we do this Schur estimator, which is an unbiased risk estimator to choose things adaptively. So in practice, we do try to do it adaptively. And we did the budget of 10 to the 1,000 iteration. So this was the noisy image, and this is the diagonal and warm restart where you do know the true image, and this is the same thing where when you try to be adaptive, you try to choose the parameter adaptively. And I think you don't see too much, and this thing, the signal to noise ratio is essentially the same. Visually, at least on my screen, this looks a little bit better, okay, but they're very comparable. And then we try to do this in the case you use KL, and basically what you see is that the algorithm, if you know the true solution, works decently, but if you try to do adaptive, really the problem is in the model selection criterion. This Schur estimator was done for Gaussian noise, and really for KL is not the right thing to do. So it's pretty bad. And again, the take-home message here is mostly that you can implement it. It just gives reasonable result, and it's on par with actually a good algorithm, the warm restart accelerated method for Tikhonov. And then I think the main thing that makes it a bit underperforming is that you have to twiddle around with this lambda t sequence. All right, so I'm strangely, I think, on time. So what's the story here? Again, the idea is that you somewhat can combine, again, optimization with modeling and try to get 2 for 1, okay, like the soap at the supermarket. And this gives you, what you gain is really not on the, say, what in this workshop would be the statistical part here is in the error estimates part, is really more about in the joint enterprise between computational complexity and noise. This, as you see, is not closing the story, but is an attempt to go towards a more general theory. And so we have some assumption on the loss and the norms, and much remains to be done. And the main point here is, I hope, is because I have endless discussion with some of my friends, it's not about the early stopping. It's really about more the fact that the optimization path is a way to search a space of solution in a biased way that gets you to specific subset of solution, and possibly, if it's needed, to stop early to ensure stability. Okay, so it's really both ingredients. I think the really fascinating fact is that optimization just doesn't wander around. It goes around in a kind of a orderly way. What can I do with this? I think one low-hanging, well, I'm not sure it's low-hanging. I think it's very hard, but there are some results. If you have in mind L1, it would be to do L1 stuff, okay? And if you can do L1 stuff, maybe then you can do matrix stuff, then you can do tensor stuff, and you can do a lot of other things. And Patrick Varun and their student have the result. And there is an older paper by Yuan Yao and co-authors. There is one more zero here, as you might have guessed. All right, so the algorithm they use in it's quite a bit different from the one we use here. This one is more similar, but we don't understand their proof. And then there are more things. Of course, there was no learning and no statistics here. You can start to add learning. You can start to do at least noise, stochastic noise, but also sampling. You start to look at classification. There are all these nice results there. So the implicit bias of logistic regression, but it's in a very specific setting, like noiseless, only for the empirical error. What about the test error? What about the future result? And then, of course, everything here was not only convex, but also the model were linear. So you can try to look at nonlinear models. And again, there are tons of results in inverse problems. There are books about implicit regularization for nonlinear problems, but also look at non-convex problem or not. So as I said, we'll see next. All right. I'm saying.